Yeah. Okay, and thank you very much for the hospitality. So I will continue with the objects that we studied last time. And then I mentioned that when we consider smaller families of spheres, it may be possible to obtain LP estimates with the LP operator norm doesn't blow up as delta goes to 0. Okay. So I will start by maybe specifying what I mean by that and what I mean by considering smaller families of spheres. Okay, so I will start by considering the units, excuse me, the unit radius case. So when we consider a point x and a unit sphere passing through that point, okay, each of given such sphere can be identified with a unit vector, okay, u, okay, or some u. Right? So yeah, considering all such sphere amounts to considering every u, every translation vector in the unit sphere. Okay. So we can rewrite n delta to be the premium, okay, over averaging of f at x plus u and where we integrate over the delta neighborhood of the unit sphere. Okay. And here we take premium over all unit sphere. Okay. And this becomes the maximal function that I introduced in the last lecture. They are the same thing. So this gives us natural way to reduce the families of sphere. Okay. So what we do is simply replace this set of sphere by arbitrary set of vectors. Okay. And then we consider premium over this set P. Okay. And here, P will be any subset of Rn. Okay. And then I will call this maximal function with n delta t. So this is a maximal function that we will be considering. So as I mentioned before, when t is Sn minus 1, and delta t is the same as n delta. Okay, and the problem is for which t, or which subset of Rn, okay, the LP operator norm of this maximal function, it does not blow up as delta goes to 0. So when is this finite? Okay. Okay. So let me also consider the limiting case, delta goes to 0 version of this operator. So we don't take average over annulus, so we just take the average over sphere. Okay. Here, this sigma is the normalized surface measure on the unit sphere. Okay, and let me denote this by, okay, this can be rewritten as F convolved with sigma evaluated at x plus u. So we are taking supremum over a set of translation vectors. And one thing that we can notice is that this maximal function controls this maximal function in the way that this operator norm is bounded by LP operator norm in the limiting case. Okay. So it suffices to consider this maximal function and ask for which T is this maximal function bounded on some LP for some finite P, and then what should be the optimal range of P, and what determines the range of P, which characteristics of T determines the range of boundedness. Okay. So it turns out that a relevant property of the set T to the boundedness of the maximal function is the delta covering number. So NP delta will denote the minimal number of delta balls, meaning balls of radius r, needed to cover the set T. For example, when T is a unit sphere, excuse me, and T delta will be comparable to delta to power minus n minus 1, okay, dimension of that set. Okay. Then our theater, joint work with Ellen Zhang and George Dosidis and myself, says that when n is bigger than 1 and T is a set satisfying this condition. So here we require this to be up to delta to power minus s. Okay. For some s less than, strictly less than n minus 1. Okay, sorry. And there is some exponent in between 1 and 2, such that this maximal function is bounded on LP for P bigger than that exponent, P and S. So it is necessary to consider S less than n minus 1. Otherwise, this result will fail to hold. Okay, so this equality case corresponds to this case with, and we already know that this operator cannot be bounded on LP for any finite P. Okay, are there any questions so far? Okay, and we give explicit exponent P. So for S in between 0 and 1, P and S yes, 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 or unit spheres, yes. Yeah. So when S is in between 0 and 1, the exponent is this one, and this exponent is optimal. Okay. But for other case, okay, so this in particular take care of the n equal to 2 case, because when n is equal to 2, s is just in between 0 and 1. Okay. But in higher dimensions, we don't expect that this exponent is optimal. Yeah. Oh, okay, so so that's a good question. So for the equality case, we are not sure, but yeah, we expect that equality case might fail to hold. Yes, but yeah, we don't have proof. So, yeah. But in terms of this strict inequality, this exponent is best possible. And yeah.
So for example, if I take a spherical cup, I get the same as the spherical cup. I get the same bounce.
Right. If you take spherical cap, yeah, you will still have this estimate. So it will fail to be bounded on any p. Okay. Okay. Yeah, as far as I remember, we take same examples. For example, on the plane, we take delta ball, and then in higher dimension, we consider delta tubes. Yeah, and I think we was able to obtain necessary condition based on similar examples. Okay, right now, but okay, the proof of this result is quite similar to the proof of the boundedness of spherical maximum function. So I will briefly sketch the proof of this result. Okay, so first we use Ricciardo-Paley theory. So I will denote by psi j such that psi j hat is supported on the dyadic annulus for j bigger than 0. When j is 0, it's compactly supported near the origin. And then we can also require that the sum of psi j had to be 1. So we decompose the measure sigma by using convolution with psi j and call this to be sigma j. Okay. And let me recall some basic bounds for sigma j. So first, sigma j behaves like the characteristic function of the unit sphere, delta annulus of the unit sphere divided by the measure of the delta neighborhood of unit sphere, plus some singular terms with exponential decay. Okay, so in practice, we may assume sigma j behaves like this one, although it's not compactly supported. And secondly, let me recall that due to the decay of the Fourier transform of the spherical measure on the sphere, we have the bound for this object. So this decays like 2 minus j times n minus 1 over 2. Right, so this gives us way to decompose MTF. So this is bounded by primum of U. Let me start with code here. Okay, so if we define MTJ, then we look at the sigma j here. Okay, then it suffices to control this object. So here is one lemma. So we first have L1 to L1 estimates, and the operator norm can be bounded by 2 to power j and times the minimum of 1 and s. So when s is small, we use 2 to sj, but when s is bigger than 1, we just use 2 to power j. Okay. And the second estimate is L2 estimates. We have 2 to minus j n minus 1 minus s. So in particular, when s is smaller than n minus 1, we can sum this over j using exponential decay, so that will give us L2 boundedness of this operator. And then we observe why we required s to be less than n minus 1. Yeah. Okay, and there are further bounds. Okay, we have there are further as we have bound and 4 over 3 bounds. Are also used. Okay, and let me just mention what they are. So if we go back to the case of m delta, okay, when we consider all the unit sphere passing through the point x, we talked about this bound for n equal to 3 and n bigger than or equal to 4. Okay. And these estimates continues to hold in this setting whenever t satisfies this condition. And then we can use that to obtain certain similar as we have and 4 over 3 bounds for this maximal function. But I'm not going to maybe write down here, but that gives a certain improvement compared to just interpolating these two estimates. Okay. This one, yeah. Well, okay, let me see. Yeah, thank you. Thank you for the correction. Yes. Yeah, we need 1/2 here. Yes. Okay. So I will just briefly mention L2 estimates. So how we approach this problem is that F convolved with sigma j is Fourier supported on annulus of radius 2 to power j. So this is a roughly constant. On both radius 2 to power minus j. So this is a heuristic for uncertainty principle, which can be made precise. So instead of taking supremum over all t, we can replace t by tj, where tj is the set of maximal 2 to minus j separated set of points on t. Okay. And then we know how many points can there be by our assumption. This is bounded by 2 to the power minus j minus s, which is 2 to the power js. Okay, so the supremum of the object squared. Okay. This is almost the same as supremum over tj. So let me take square here. Okay, and then we just sum the bound this by sum over u in tj. So this is not very rigorous, but it can be made precise. But roughly speaking, this is the main idea here. And then in this form, we can integrate over x. And then the number of terms will be 2 to the power js. And then combined with this decay of the Fourier transform, we can obtain the L2 estimates. Right, any questions so far? Okay, and let me move on to now the case when we consider spheres of radius 1 and 2, between 1 and 2, comparable to 1. Okay, so for S delta, let me define this one into this one notation. So AVGF xt will denote the average of this function over the sphere of radius t, centered at the point x. Okay, and by using similar procedure, we can consider, it suffices to consider this operator as T. Okay, where we take primum of the average of the function f, with sphere centered at x plus tu with the radius t. And here we have additional primum over t. That's the maximum function corresponding to S delta. So when T is the unit sphere, then ST is the delta goes to 0 version. The version of S delta by our choice of this maximum function. And when T is the set only containing the origin, but then this take average over sphere centered at the point x. So this corresponds to the spherical maximum function. Classical spherical maximum function. And it is well known in this case that ST is bounded on LP if and only if P is bigger than n over n minus 1, okay, which is due to Stein and again. Okay, then about that operator, we prove similar bounds. So here T is a subset of Rn such that NT delta covering number is bounded above by delta to the power minus S. By the way, when I say this, I mean this holds for any delta in between 0 and A1/2, with some constant which does not depend on delta. Okay, again, we assume this for some S less than n minus 1 and in between 0. Okay. And this operator is bounded on LP for P bigger than another constant P and S, which is natural in the sense that when you take the limit of this exponent as S goes to 0, we get n over n minus 1. Okay, so this corresponds to spherical maximum function. And on the other hand, when you take the limit as the s goes to n minus 1, okay, so this case corresponds to the maximum function s delta. Okay. So in this case, we get exponent 3 in dimension 2 and 2 in higher dimensions. Right, and this exponent is optimal in certain cases, but I think it should be improved in general. Okay, and right, for this problem, we use an approach which is different from the approach we take for the maximum function np. So if we apply the previous approach to this maximum function, then we get some suboptimal estimates. So we use some different approach here, and it can be summarized as, so we reduce this problem to LP estimates for solutions to wave equation over fractal measures. Okay. So I will now explain what we mean by that for the remaining talk. So for the case of spherical maximum function, boundedness property of spherical maximum function can be obtained from local smoothing estimates for the wave equation. That was observed by Seeger, Salk. Mohali. Mohali, Seeger, and Salk. Thank you. So, and then we somehow obtain some analog of those results in the case of this maximum function, where we have additional supremum over this sort of translation. Okay. First, we use linearization. So here, given measurable functions, u, let's map Rn to T, and then T to a unit interval. Over u and t, okay, by considering arbitrary measurable functions u and t. Okay, then the goal is to prove LP operator, LP estimate for this linearized operator. Okay, with some constant times 2 to power minus the epsilon j, with some exponential gain in j, so that we can sum this over all j. So here I forgot to write down problem for the Schrodinger maximum function. This idea has also been used. And in that case, when we take premium over T, we take, when in R plus 1 dimensional, so we can consider measure which is 1 dimensional lower in that when we only consider premium over T. And now we take premium over T as well as set of translation U. And so what type of measure we will get? Okay, so Ricci Markov Katutani representation. On this space. Yeah, so, okay. The reason that we consider this linear functional is that when and in this case, compact set on Rn. Okay, and the Ricci Markov Katutani representation theorem can be realized as integral of f under this measure. Okay, and what we can say about this measure, so that's key point of our reduction. So uh, 0 and 1. Okay, and here the crucial thing is that this constant is independent of the choice of the measurable functions u and t. Okay. So I'm going to use a notation. So whenever measure non-negative Fourier measure satisfy this condition, and I will say mu is in C alpha. Okay, I denote this condition by mu in C alpha. Support of mu, yeah, we can assume that mu lives on a unit ball times in time interval from 1 to 2. Yeah. For, yeah. Yeah, when S is 0, it could be N, but you mean this alpha? Yes, yes. So this. Not full household dimension. I'm not sure if I understand your question. Yeah. Mm-hmm. Yeah. Yeah, so I'm not sure, but roughly speaking, I think of mu as supported on some alpha dimensional set on unit ball. Yes, in Rn plus 1. Okay, so we have reduced this the problem to this estimate, and then by this observation, so it suffices to show that the LP norm over measure mu is bounded by 2 to minus epsilon j. Okay, for any mu in the class C alpha, with alpha equal to n minus s. Okay, so we just use this function over here and then use this comparability. And here we assume that this implicit constant should be independent of the choice of this measure. It only depends on this alpha and j and dimension. Okay. Okay, now let me recall that the spherical measure can be decomposed or can be written in this form, e to I c with some symbol a plus, e to minus I c with another symbol. Okay, each of them satisfy the standard estimate. Okay. So using this, let me denote this equation by R2. And R2 can also be written as 2 to power minus j and minus 1 over 2 with e to it square root of minus Laplacian, which is so-called half-wave operator. And then we look at this LP norm over this measure. And then it suffices to prove this estimate. Okay, so the question is, for which P is this estimate true? Let me call this to be R3. Okay. And I should say not much is known about this problem. Okay, this even for the case mu is the Lebesgue measure. Okay, so not much is known. So even when mu is the Lebesgue measure, on Rn times 1, 2, the optimal estimate, LP estimate for this the optimal bounds for the ratio between this norm, LP norm, with LP norm of F is a difficult open problem. in dimension n bigger than 2. Okay, but in the case of dimension 2, when n is dimension 2, this sharp estimate is known, which is due to due to Goose, Wang, and Zhang. So in the dimension 2 case, the critical exponent P here is 4. And then they can bound this expression by 2 to power epsilon j, or arbitrarily small epsilon. So that's their result. So in higher dimensions, there are similar conjectures regarding this estimate. And then, and this estimate is known to imply other conjectures in harmonic analysis, like Bochner-Riesz or restriction conjecture. Okay, so this, all right, now let me mention what else is known about this problem. When the dimension is 2 and P is equal to 2, I think there are earlier work due to Wolf and Erdogan about this type of problems. And then more recently, there is work by Ham and Kaur and Lee. And they considered this problem. So they proved the estimate written over there for P bigger than 4 minus alpha, where alpha is in between 3 minus root 3 and 2. Okay. And they obtain sharp estimate in between alpha in between 2 and 3. And that follows from the work of Goose, Wang, and Zhang. And in their work, they used their L4 estimate, as well as Bennett-Carberry-Tau multilinear restriction estimate for the cone, combined with Brudengo's induction on scales argument. So that's where they obtained this estimate. And this estimate gives us some sharp exponent P and S that I talked about earlier, but only for some restricted range of this dimension constant S. Okay. And then we also studied this problem. So we use this problem, this result. And also we studied relationship between this type of estimates with LP estimates for the sum of characteristic functions of delta annulus. So such as we have seen before, which is due to Wolf and Harmonic, Yang, and Zhao result. So we are able to make some equivalence between this type of estimate with estimate that we have seen earlier in the first talk. And so we were able to do say something about alpha equal to 1 case. So from Wolf, Harmonic, Yang, and Zhao result. that we talked about last time. Okay, and then we see when alpha is 1, the exponent is 3, which matches with that exponent. Okay, but let me just stress that getting sharp bound for this one is wide open for any alpha in between 1 and 2 in the dimension 2 case. And I think much less is known in higher dimensions. Okay, let me stop here. Thank you very much.
So any question from the online participants? There's no online? Okay, let us go.
So I have a question. So for dimension n equal to 2, the
Yeah.
optimal estimates for this estimate gives the optimal exponent for the LP boundedness of ST. So in the case n equal to 2, is it optimal?
Sorry, can you
In the
repeat?
case when the dimension is n equal to 2,
Yes.
is the LP boundedness of the operator ST, is it optimal?
Yes, optimal as long as alpha, which is in our case 2 minus s,
Okay.
belongs to this interval.
Okay.
Yeah. And additionally, when we have alpha equal to 1 case, in that case, these are essentially optimal.
Okay.
But yeah, what's somewhat mysterious is what happens in between alpha from 1 to remaining part.
Okay. Thanks.
Yeah, actually, basically the extension of that problem, that question. So do you think that the sharp estimate for R3 will imply the sharp estimate for ST? Sharp estimate
For R3,
R3
yeah.
will imply the sharp estimate for the maximal operator ST?
At least for n equal to 2, yes, I think this will, yeah, sharp estimate on R3 will give sharp estimate for P and S in dimension 2. Yeah. For higher dimensions, I'm not so sure.
Okay. Thank you.
Any question?
One more question. So the measure nu that we are getting from the linear functional, so it satisfies the growth condition, like the volume of the ball is less than r to the power alpha, and alpha has this s, right, n minus s, and this s is the dimension of the set T.
Yeah, we can think of, yes.
Yeah.
that's
So
the
is
dimension.
that observation easy to see? I mean, using the linear functional, or is it?
I would say it's not trivial, but it's not so difficult. I
Okay.
would say, yeah,
Okay.
it's doable. Yeah.
Okay. Thanks.
And then we realized this. Okay, before we observed this, we did some similar computation for the operator n delta t or s delta t. Yeah, and then what we there realized was that whenever t satisfies this condition, whenever t satisfies these conditions, all the estimates that we obtain for S delta and N delta continues to hold for in this setting. So yeah, I think maybe here we observed some properties, some connection between this type of estimate and dimension of T.
Conclude this session, giving thanks to President Son for his wonderful lecture.
Okay, thank you.
Go for lunch.